What if everything we thought we knew about space travel was just the beginning? For centuries, humanity has dreamed of reaching the stars, but the universe has always seemed just out of grasp, held back by one unbreakable rule: the speed of light. Yet, what if light speed isn't the ultimate barrier? What if there are ways to bend, twist, or even bypass the laws of physics as we know them? Today, we're diving into 25 unconventional theories on propulsion that could rewrite the rules of space travel. From mind-bending concepts like warp drives to the idea of manipulating spacetime itself, these theories aren't just science fiction. They're the bold, imaginative steps that could one day take us to the farthest corners of the cosmos. So buckle up. We're about to explore ideas that could change not just how we travel, but how we see the universe itself. Imagine a spacecraft not racing through space, but gliding effortlessly on a wave of warped spacetime itself. This is the heart of the Alcubierre Drive, a concept that doesn't try to break the speed of light. It sidesteps it entirely. Instead of pushing a ship faster and faster, the Alcubierre Drive envisions compressing the space in front of the vessel while expanding the space behind it. Picture it like riding a cosmic surfboard, where the wave of spacetime does the heavy lifting, carrying the ship forward without violating Einstein's laws of relativity. The idea, first proposed by physicist Miguel Alcubierre in 1994, is rooted in Einstein's theory of general relativity, which describes how massive objects bend the fabric of spacetime. If we could manipulate spacetime in this way, a ship could effectively travel faster than light without actually moving through space at all. It's not about speed, it's about bending the rules of the universe itself. But here's the catch: to create this kind of spacetime warp, we'd need something called exotic matter, a theoretical substance with negative energy density. This exotic matter would have properties unlike anything we've ever observed, like repelling gravity instead of attracting it. While we haven't found or created such material yet, scientists are exploring whether quantum effects or advanced technologies could one day make it possible. The Alcubierre Drive isn't just a wild idea. It's a spark of inspiration that keeps researchers pushing the boundaries of what we think is possible. And while the challenges are immense, the potential is staggering, a way to explore the stars without being bound by the speed of light. But what if bending spacetime isn't the only way to rewrite the rules of space travel? What if we could twist the universe in an entirely different way? Stay tuned, because the next theory might just blow your mind. What if the vast distances between stars weren't as insurmountable as they seem? Enter Wormholes, hypothetical tunnels through the fabric of spacetime that could act as cosmic shortcuts, cutting travel times from millennia to mere moments. Picture a sheet of paper folded in half with a pencil poking through from one side to the other. In this analogy, the pencil is the wormhole, bypassing the long journey across the surface of the paper. It's a concept that sounds like science fiction, but it's rooted in the same mathematical framework as Einstein's theory of general relativity. Wormholes, also known as Einstein-Rosen bridges, were first theorized in 1935 as solutions to Einstein's equations. These theoretical tunnels could connect two distant points in spacetime, potentially allowing for instantaneous travel across the universe. But here's the twist: while the math checks out, the real-world practicality is far from certain. Just like the Alcubierre Drive, wormholes would require exotic matter to remain stable, a substance with negative energy density to keep the tunnel from collapsing under its own gravitational forces. The challenges don't end there. Even if we could find or create exotic matter, wormholes would likely be incredibly unstable, prone to closing or ripping apart anything that tried to pass through. And then there's the question of where they might lead. Could a wormhole connect two points in our own universe, or would it open a gateway to an entirely different dimension? These are the kinds of questions that keep physicists and science fiction writers alike captivated. Despite the speculative nature of wormholes, they remain a tantalizing possibility. They represent a fundamentally different approach to space travel, one that doesn't rely on speed or propulsion, but instead manipulates the very fabric of the universe. And while the debate over their existence and practicality continues, wormholes remind us that the universe might be far stranger and more interconnected than we ever imagined. But wormholes aren't the only way to rethink the rules of space travel. What if the key to interstellar exploration lies not in bending space-time but in harnessing forces we've only just begun to understand? The next theory takes us into the realm of quantum physics, where the rules of the game are entirely different. Now, let's step into the bizarre and fascinating world of quantum entanglement, where particles millions of light-years apart can influence each other instantaneously. This strange phenomenon, often called spooky action at a distance by Albert Einstein himself, could hold the key to a revolutionary form of propulsion, or at least a way to communicate faster than light. Here's how it works. When two particles become entangled, their properties like spin or polarization become linked, no matter how far apart they are. Change one and the other changes instantly, breaking the usual rules of time and space as we understand them. At first glance, this seems like the ultimate cheat code for interstellar travel. Imagine sending information across the galaxy in the blink of an eye, with no need for signals to crawl at the speed of light. A spacecraft equipped with entangled particles could, in theory, receive instant updates or commands from Earth, making navigation and coordination over vast distances far more efficient. But before we get too excited, there's a catch. While entangled particles can share information instantaneously, we can't actually use them to send messages in the traditional sense. The act of measuring one particle affects its entangled partner, but the results are random, making it impossible to encode meaningful data directly. Despite this limitation, scientists are exploring ways to harness quantum entanglement for practical applications. Some have proposed using entangled particles to create a kind of quantum GPS, where measurements could reveal changes in space-time or gravitational fields, aiding navigation in deep space. Others suggest that entanglement might play a role in advanced propulsion systems, though the specifics remain speculative. The challenge lies in scaling up this delicate quantum phenomenon. Entanglement is notoriously fragile, easily disrupted by external forces, and maintaining it over long distances, let alone across the vastness of space, is a monumental task. And then there are the ethical questions. What happens when we start manipulating the quantum fabric of the universe? Could tampering with entangled states have unintended consequences, like disrupting the natural balance of particles or even space-time itself? These are the kinds of questions that keep physicists and philosophers awake at night, reminding us that every leap forward comes with its own set of risks and responsibilities. Quantum entanglement propulsion remains a tantalizing but elusive idea, one that pushes the boundaries of our understanding of physics. But while it may not solve the speed of light problem directly, it opens up a whole new realm of possibilities for how we might one day explore the cosmos. And speaking of possibilities, what if the key to faster-than-light travel isn't about manipulating particles or space-time at all? What if it's about unlocking the secrets of energy itself? That's where our next theory takes us into the realm of energy manipulation, where the very forces that power the universe might hold the answers we've been searching for. What if the fuel for our interstellar dreams was something so powerful, so volatile, that a single gram of it could outshine the energy of an atomic bomb? This isn't science fiction, it's antimatter, the most energy-dense substance we know of. When antimatter meets matter, the two annihilate each other in a burst of pure energy, releasing a staggering amount of power. For space travel, this could be a game changer. Antimatter propulsion harnesses this explosive reaction, offering the potential to propel spacecraft to near-light speeds with efficiency far beyond any chemical rocket. The concept is simple in theory. Direct the energy from matter-antimatter annihilation to create thrust. The result, a propulsion system that could slash travel times across the solar system from years to months or even weeks. Imagine a trip to Mars taking just a fraction of the time it does today, or a voyage to the outer planets becoming a routine mission rather than a decades-long endeavor. The possibilities are as thrilling as they are revolutionary, but here's the catch: antimatter is incredibly difficult to produce and even harder to store. Right now, we can only create tiny amounts of it in particle accelerators, and at a cost that makes gold look cheap. To make matters worse, antimatter is highly unstable. It can't touch anything made of ordinary matter without annihilating instantly, which means containing it requires magnetic fields so precise that even the slightest error could result in catastrophic energy release. Despite these challenges, scientists aren't giving up. Experiments like those at CERN are exploring ways to produce and trap antimatter more efficiently, and researchers are investigating how to convert its energy into usable thrust without destroying the spacecraft in the process. Some have even proposed using antimatter to trigger fusion reactions, amplifying its power even further. While we're still far from practical antimatter propulsion, the progress being made is a testament to human ingenuity and our relentless drive to explore the unknown. Antimatter propulsion represents a bold step forward, but it's not without its risks and limitations. And while it's one of the most promising ideas for near-light-speed travel, it still relies on conventional energy sources, albeit in an extreme form. So, what if there's a way to move through the cosmos without relying on energy as we know it at all? What if the key to faster-than-light travel lies in something even more mysterious? That's where our next theory takes us, into the realm of the truly unconventional. What if the key to interstellar travel wasn't locked in the stars themselves, but in the very fabric of the cosmos? Enter dark energy, the mysterious force that's causing the universe to expand at an accelerating rate. Discovered in the late 1990s, dark energy makes up about 68% of the universe, yet we know almost nothing about its true nature. It's invisible, intangible, and seemingly everywhere, pushing galaxies apart faster than gravity can pull them together. But what if we could tap into this cosmic force to propel spacecraft across the void? The idea of a dark energy drive revolves around harnessing this expansion to surf on the stretching fabric of space-time. Imagine a ship not powered by engines or fuel, but riding the wave of the universe's expansion itself. Instead of fighting against the limits of physics, such a spacecraft would align itself with the natural flow of the cosmos, using the push of dark energy to achieve speeds that defy conventional propulsion. It's a concept that feels almost poetic, turning the universe's own momentum into a tool for exploration. But here's the challenge: we don't even know what dark energy is. Is it a property of space itself, as Einstein's cosmological constant suggests? Or is it some kind of exotic field or particle we've yet to discover? Without understanding its fundamental properties, the idea of harnessing dark energy remains purely speculative. Scientists are still grappling with how to detect it directly, let alone manipulate it. And even if we could, the sheer scale of dark energy's influence stretching across the entire universe makes the idea of controlling it for propulsion seem almost absurd. Despite these hurdles, the concept of a dark energy drive sparks the imagination. It represents a shift in how we think about space travel, not as a struggle against the universe, but as a partnership with its natural forces. It's a reminder that the cosmos is full of mysteries waiting to be unlocked, and that the answers to our greatest challenges might lie in the very fabric of reality itself. Of course, dark energy isn't the only force we could potentially harness. While its enigmatic nature makes it a tantalizing but distant possibility, other theories focus on manipulating forces we already understand, or at least think we do. From gravity to electromagnetism, the universe is filled with phenomena that could one day revolutionize how we explore the stars. So, as we leave the speculative realm of dark energy behind, let's turn our attention to something a little more grounded yet no less extraordinary. What if the key to interstellar travel wasn't a massive rocket but a beam of light? Imagine harnessing the power of lasers to propel spacecraft to incredible speeds, turning photons into a cosmic wind that could carry us to the stars. This is the promise of laser propulsion, a concept that replaces traditional fuel with focused beams of light to push spacecraft forward. Instead of relying on bulky engines or chemical reactions, a laser propulsion system would use the momentum of photons themselves to accelerate a ship, potentially reaching a significant fraction of the speed of light. One of the most ambitious projects exploring this idea is Breakthrough Starshot, a bold initiative aiming to send tiny, lightweight probes to Alpha Centauri, our nearest star system, in just 20 years. These probes, each no larger than a postage stamp, would be equipped with reflective sails designed to catch the force of powerful ground-based lasers. When the laser arrays fire, their beams would strike the sails, transferring momentum and pushing the probes to speeds of up to 20% the speed of light. At that pace, the journey to Alpha Centauri, 4.37 light-years away, could take just over 2 decades, a blink of an eye compared to traditional methods. But as thrilling as this concept is, the challenges are immense. To achieve the necessary thrust, the lasers would need to be unimaginably powerful, requiring arrays spanning kilometers and consuming vast amounts of energy. The materials used for the sails would also need to be incredibly lightweight yet durable enough to withstand the intense laser bombardment without melting or tearing. Even the slightest imperfection in the sail's design could cause it to fail catastrophically, sending the probe spinning off course or disintegrating entirely. And then there's the issue of aiming. Over interstellar distances, even the tiniest misalignment of the laser beams could mean missing the target entirely. Despite these hurdles, Breakthrough Starshot represents a leap forward in how we think about space travel. It challenges us to move beyond the limitations of chemical rockets and explore entirely new ways of reaching the stars. And while the project is still in its early stages, it's a reminder that sometimes the most groundbreaking ideas come from reimagining the tools we already have. But what if we didn't need powerful lasers or external propulsion systems at all? What if the spacecraft itself could generate the energy it needs to travel at incredible speeds? That's where our next theory takes us, into the realm of self-sustaining propulsion, where the boundaries of physics and engineering are pushed to their absolute limits. Picture a spacecraft that generates thrust without expelling any fuel, no rockets, no exhaust, just a device that seems to bend the rules of physics as we know them. This is the promise of the M-Drive, a propulsion concept that has sparked both excitement and skepticism in equal measure. At its core, the M-Drive, short for electromagnetic drive, claims to produce thrust by bouncing microwaves within a closed, cone-shaped cavity. According to its proponents, this creates a net force in one direction, effectively propelling the spacecraft forward without the need for propellant. If true, it would defy Newton's third law of motion, which states that for every action, there must be an equal and opposite reaction. The idea of a reactionless drive is nothing short of revolutionary. Traditional rockets rely on expelling mass to generate thrust, which limits their efficiency and requires massive amounts of fuel. The M drive, on the other hand, suggests a way to bypass this limitation entirely, potentially opening the door to lighter, faster, and more efficient spacecraft. It's a concept that could redefine how we think about propulsion, making long-distance space travel far more practical than ever before. But here's where things get contentious. The M drive has been the subject of fierce debate within the scientific community. Critics argue that if the drive works as claimed, it would violate fundamental laws of physics, particularly the conservation of momentum. How can a closed system generate thrust without expelling anything? Skeptics point to the possibility of experimental errors or unaccounted-for external forces, suggesting that the observed thrust might be the result of measurement anomalies rather than a genuine breakthrough. Despite the skepticism, some experimental results have kept the conversation alive. In 2016, NASA EagleWorks lab reported detecting small but measurable amounts of thrust from an M drive prototype. While the results were intriguing, they were far from conclusive, and the scientific community has called for more rigorous testing to rule out any potential sources of error. Since then, independent researchers and institutions have attempted to replicate the findings with mixed results. Some experiments have shown similar thrust, while others have found no evidence of propulsion at all. The ongoing debate around the M drive highlights the tension between innovation and the scientific method. On one hand, it's a tantalizing idea that could revolutionize space travel. On the other, it challenges principles that have been the foundation of physics for centuries. Until more definitive evidence is gathered, the M drive remains a controversial and unproven concept, one that keeps scientists and enthusiasts alike on the edge of their seats. As we continue to explore the boundaries of propulsion, the M drive reminds us that sometimes the most groundbreaking ideas come from questioning the rules we thought were set in stone. And while the debate over its validity rages on, it's worth considering that the next big leap in space travel might not come from breaking the laws of physics, but from reimagining them entirely. Speaking of reimagining, what if the key to faster-than-light travel lies not in defying physics, but in unlocking a hidden dimension of reality? That's where our next theory takes us, into the realm of higher dimensions, where the universe might hold secrets we've yet to uncover. What if the most destructive force in the universe could become the ultimate engine for space travel? Black holes' cosmic vacuum cleaners with gravity so intense that not even light can escape might seem like the last thing you'd want to bring on board a spacecraft. But what if we could harness their immense power, turning them into propulsion systems capable of propelling us to the stars? Enter the concept of black hole drives, a theory that pushes the boundaries of both physics and imagination. At the heart of this idea is the notion of extracting energy from a black hole's rotation. Known as the Penrose process, this method involves sending matter into the ergosphere, the region just outside a black hole's event horizon where space-time is dragged along with the black hole's spin. If the matter splits into two particles, one can escape with more energy than it entered with, effectively stealing energy from the black hole's rotation. This process, while purely theoretical, suggests that black holes could act as cosmic batteries, storing and releasing vast amounts of energy. But why stop at natural black holes? Some theorists have proposed creating artificial micro-black holes, tiny, man-made singularities that could be controlled and used as propulsion sources. These micro-black holes would be small enough to manage, yet powerful enough to generate thrust by emitting Hawking radiation, a form of energy predicted by physicist Stephen Hawking. As the black hole evaporates, this radiation could, in theory, be harnessed to propel a spacecraft. It's a concept that sounds like science fiction, but it's rooted in the same laws of physics that govern the universe. Of course, the challenges are as enormous as the black holes themselves. Creating a micro-black hole would require technology far beyond our current capabilities, not to mention energy levels comparable to those produced by particle accelerators like the Large Hadron Collider. And then there's the question of containment. How do you keep a black hole, even a tiny one, from devouring everything around it? The risks of a runaway black hole are as terrifying as they are catastrophic, making this idea as dangerous as it is intriguing. Beyond the technical hurdles, there's the speculative nature of the theory itself. We've never observed a micro black hole, let alone created one, and the physics of Hawking radiation remains unproven. Yet the concept of black hole drives captures the imagination, offering a glimpse of what might be possible if we could master the most extreme forces in the universe. While black holes represent one of the most dramatic approaches to propulsion, they're not the only cosmic phenomena that could revolutionize space travel. Sometimes the answers lie not in the colossal, but in the subtle forces and principles that operate on scales we're only beginning to understand. And as we leave the realm of black holes behind, let's explore a theory that shifts our focus from the massive to the minuscule, where the smallest particles might hold the key to the grandest journeys. What if the universe held particles that could zip through space faster than light, defying everything we know about physics? Enter Tachyons, hypothetical particles that, if they exist, would always travel faster than the speed of light. Unlike anything we've ever observed, tachyons are a fascinating what-if in the world of quantum physics. According to some theories, these particles wouldn't just break the cosmic speed limit, they'd shatter it entirely, opening up possibilities for propulsion systems that could outpace light itself. The idea of tachyons comes from the mathematics of special relativity. Einstein's equations don't explicitly forbid particles moving faster than light. They just suggest that such particles would have imaginary mass, a concept that's as mind-bending as it sounds. Imaginary mass doesn't mean the particles are fake. It's a mathematical way of describing how tachyons would behave, accelerating as they lose energy and slowing down as they gain it. In other words, the more energy a tachyon has, the closer it gets to the speed of light, but it can never go slower than that. If tachyons exist, they could revolutionize propulsion by offering a way to travel faster than light without bending space-time or relying on exotic matter. Imagine a spacecraft powered by tachyon-based engines, hurtling through the cosmos at speeds that make interstellar travel not just possible but practical. Theoretically, such a system could bypass the energy requirements of traditional propulsion, making it a game-changer for exploration. But here's the catch: despite decades of searching, we've never found any evidence that tachyons exist. Experiments designed to detect them have come up empty, and their hypothetical nature remains just that, a hypothesis. Skeptics argue that if tachyons were real, they would have left some trace in the universe by now. Others point out that their existence could wreak havoc on our understanding of causality. If information can travel faster than light, it could lead to paradoxes where effects precede causes, turning the orderly flow of time into a tangled mess. The implications of tachyons go far beyond propulsion. If they exist, they could fundamentally alter our understanding of space, time, and the laws of physics. They challenge us to rethink what's possible and confront the limits of our knowledge. But until we find concrete evidence, tachyons remain a tantalizing what-if in the quest for faster-than-light travel. While tachyons offer one intriguing possibility, they're not the only path to reimagining propulsion. What if the key to interstellar travel lies not in particles, but in something far more abstract, a force or phenomenon we've yet to fully understand? That's where our next theory takes us, into the realm of ideas that push the boundaries of science and imagination alike. What if the vast emptiness of space wasn't empty at all? What if the void between stars and galaxies was brimming with energy just waiting to be tapped? This is the intriguing premise behind vacuum energy propulsion, a theory that suggests we could harness the energy of empty space itself to power spacecraft across the cosmos. At first glance, the idea seems almost paradoxical. How can nothingness contain energy? Yet, according to quantum mechanics, the vacuum of space is anything but empty. At the quantum level, space is a seething, bubbling sea of energy. Particles and antiparticles pop in and out of existence in fleeting moments, creating a dynamic, chaotic background known as the quantum vacuum. This phenomenon, often referred to as zero-point energy, is the lowest possible energy state of a system, yet even here, energy is present. Theoretically, if we could extract even a tiny fraction of this energy, it could provide an almost limitless power source for propulsion. The concept of vacuum energy propulsion builds on this idea, proposing that a spacecraft could tap into the quantum vacuum to generate thrust. Instead of relying on fuel or external energy sources, the ship would draw energy directly from the fabric of space itself. It's a vision of propulsion that's as elegant as it is revolutionary, offering the potential for self-sustaining, long-duration space travel without the need for refueling. Imagine a spacecraft that never runs out of energy, gliding effortlessly through the cosmos powered by the universe's own background hum. But here's the catch. While the math behind zero-point energy is well established, actually extracting usable energy from the quantum vacuum is another story entirely. The energy fluctuations in the vacuum are incredibly small and fleeting, making them difficult to harness. Current theories suggest that doing so would require technology far beyond our current capabilities, including devices capable of manipulating quantum fields on an unprecedented scale. Some researchers have proposed using advanced materials or exotic configurations of electromagnetic fields to capture this energy, but these ideas remain purely speculative. Moreover, the very nature of vacuum energy raises profound questions about the laws of physics. If we could extract energy from the quantum vacuum, would it violate the conservation of energy? Could it lead to unintended consequences, like destabilizing the fabric of space-time itself? These are the kinds of questions that keep physicists up at night, reminding us that every leap forward comes with its own set of challenges and uncertainties. Despite the hurdles, vacuum energy propulsion remains a tantalizing possibility. It challenges us to think differently about the universe and the resources it might offer. And while the idea is still in its infancy, it's a reminder that the cosmos is full of surprises, hidden potentials that could one day transform how we explore the stars. But what if the key to interstellar travel lies not in extracting energy from the vacuum, but in bending the very forces that govern the universe? What if we could manipulate gravity itself, turning it from a barrier into a tool? That's where our next theory takes us, into the realm of gravity manipulation, where the rules of the cosmos might be rewritten entirely. What if the universe itself could give us a boost, not through energy or particles, but through ripples in the very fabric of reality? Gravitational waves, massive undulations in space-time caused by cataclysmic events like black hole collisions or neutron star mergers, are among the most powerful phenomena in the cosmos. First detected in 2015, these waves confirmed a key prediction of Einstein's theory of general relativity and opened a new window into how we observe the universe. But what if we could do more than just detect gravitational waves? What if we could ride them? The concept of gravitational wave propulsion hinges on the idea of harnessing these ripples to propel a spacecraft. Picture a surfer catching a wave, but instead of water, the wave is a distortion in spacetime itself. As gravitational waves pass through the universe, they stretch and compress spacetime in their path. If a spacecraft could somehow synchronize with these waves, it could theoretically surf on them, gaining momentum without the need for traditional fuel or engines. It's a bold idea that turns the universe's most violent events into a potential highway for exploration. But how would this work in practice? One proposal suggests equipping a spacecraft with a kind of sail designed to interact with gravitational waves. Just as a sailboat catches the wind, this sail would catch the ripples in spacetime, using their energy to propel the ship forward. Another idea involves creating artificial gravitational waves, perhaps through advanced technology or by manipulating massive objects to generate a controlled wavefront for propulsion. The possibilities are as intriguing as they are speculative. However, the challenges are immense. Gravitational waves are incredibly faint by the time they reach us, requiring highly sensitive instruments like LIGO to detect them. Harnessing their energy for propulsion would require technology far beyond our current capabilities, not to mention a deep understanding of how to interact with spacetime distortions on such a scale. And then there's the question of control. How do you steer a spacecraft on waves that are unpredictable and fleeting? Despite these hurdles, the idea of gravitational wave propulsion sparks the imagination. It represents a shift in how we think about space travel, not as a battle against the universe, but as a dance with its rhythms. It's a reminder that the cosmos is full of untapped potential, and that the answers to our greatest challenges might lie in the very forces that shape the universe. While gravitational waves offer one tantalizing possibility, other theories focus on harnessing subtler forces phenomena that operate not on the grand scale of black hole collisions, but on the delicate interplay of particles and fields. As we move from the colossal to the intricate, the next theory invites us to explore how the smallest interactions might hold the key to the grandest journeys. Imagine a spacecraft gliding silently through the void, powered not by roaring engines or explosive fuel, but by the gentle push of sunlight. This is the elegance of solar sails, a propulsion method that turns the faint pressure of light into a cosmic wind. Unlike traditional rockets that burn through fuel at an alarming rate, solar sails rely on the nearly limitless energy streaming from stars, offering a sustainable and fuel-free way to explore the cosmos. It's a concept that feels almost poetic, transforming something as intangible as light into a tangible force for movement. The principle behind solar sails is surprisingly straightforward. Photons, the tiny particles that make up light, carry momentum despite having no mass. When these photons strike a reflective surface, like the sail of a spacecraft, they transfer a small amount of that momentum, creating a gentle but continuous push. Over time, this pressure can accelerate a spacecraft to incredible speeds, especially when harnessed close to a star where light is most intense. It's a bit like a sailboat catching the wind, but instead of air, the sail is propelled by starlight. One of the most exciting demonstrations of this technology came from the Light Sail project, led by the Planetary Society. In 2019, Light Sail 2 successfully deployed its reflective sail in Earth's orbit, proving that sunlight alone could be used to change a spacecraft's trajectory. The mission was a milestone, showing that solar sails aren't just theoretical, they're a practical and promising tool for future exploration. Projects like these pave the way for missions to distant destinations, where carrying massive amounts of fuel would be impractical or impossible. But solar sails aren't without their challenges. Their effectiveness depends heavily on proximity to a star, meaning they work best in the inner solar system or near other bright stars. As a spacecraft ventures farther from a light source, the pressure from photons diminishes, slowing acceleration and limiting the sail's usefulness. Additionally, solar sails are incredibly lightweight and delicate, making them vulnerable to damage from micrometeoroids or intense radiation. And while they offer a sustainable way to travel, they're not exactly quick. Building up significant speed takes time, and interstellar voyages would still require years or even decades. Despite these limitations, solar sails represent a bold step toward sustainable space travel. They remind us that the universe is full of untapped resources, waiting for us to find creative ways to harness them. And while they may not be the solution for every mission, they open up possibilities for exploration that were once thought impossible. But what if we didn't need to rely on starlight at all? What if there were a way to generate propulsion without depending on external energy sources? That's where our next theory takes us into a world where the boundaries of physics and engineering are pushed to their absolute limits, offering a glimpse of what might be possible when we think beyond the stars. What if the key to interstellar travel was hidden within the very heart of a star? Fusion propulsion takes inspiration from the cosmos itself, harnessing the same process that powers stars to propel spacecraft across unimaginable distances. At its core, fusion is the process of combining light atomic nuclei like hydrogen to form heavier elements, releasing a staggering amount of energy in the process. This is the same reaction that keeps stars burning for billions of years, and it's a potential game changer for space travel. The promise of fusion propulsion lies in its efficiency. Traditional chemical rockets burn fuel to generate thrust, but they're limited by the amount of energy stored in chemical bonds. Fusion, on the other hand, taps into the energy locked within atomic nuclei, offering millions of times more energy per unit of fuel. Imagine a spacecraft powered by the same forces that light up the universe, able to travel farther, faster, and with far less fuel than anything we've built before. But here's the challenge: replicating the conditions inside a star on a spacecraft is no easy feat. Fusion requires extreme temperatures and pressures to force atomic nuclei together, overcoming their natural tendency to repel each other. On Earth, we've made progress with experimental fusion reactors like tokamaks and stellarators, but these devices are massive and energy-intensive, far from the compact systems needed for space travel. Creating a fusion reactor small and efficient enough to fit on a spacecraft is one of the greatest engineering challenges of our time. Despite these hurdles, researchers are making strides. Projects like the Direct Fusion Drive, being developed by Princeton Plasma Physics Laboratory, aim to create compact fusion reactors specifically designed for propulsion. These systems would generate both thrust and electricity, making them ideal for long-duration missions. If successful, fusion propulsion could slash travel times to Mars from months to weeks, or even make interstellar missions feasible within a human lifetime. The potential of fusion propulsion is as vast as the stars themselves, but it's not the only path to reimagining how we explore the cosmos. What if there were a way to travel faster than light without relying on nuclear reactions at all? That's where our next theory takes us into a realm where the boundaries of physics and imagination blur, offering a glimpse of what might be possible when we dare to think beyond the stars. Imagine a world where magnets didn't come in pairs, where you could have a North Pole without a South, or a South Pole without a North. This isn't just a thought experiment. It's the essence of magnetic monopoles, hypothetical particles that could rewrite the rules of magnetism as we know them. Unlike the magnets we're familiar with, which always have two poles, monopoles are theorized to carry just a single, isolated magnetic charge. If they exist, these elusive particles could unlock entirely new ways to generate and manipulate magnetic fields, potentially revolutionizing propulsion and energy systems. The idea of magnetic monopoles traces back to the early days of quantum mechanics. In the 1930s, physicist Paul Dirac proposed that the existence of monopoles could explain why electric charge comes in discrete, quantized units. His equations suggested that monopoles would be incredibly massive particles, far heavier than anything we've discovered so far. Yet, despite decades of searching, no one has ever observed a magnetic monopole in nature or in experiments. They remain a tantalizing what-if, a puzzle piece that could complete our understanding of the universe or challenge it entirely. So, what makes monopoles so intriguing for propulsion? One possibility lies in their ability to create incredibly strong and stable magnetic fields. If we could harness monopoles, we might develop propulsion systems that use magnetic fields to generate thrust without the need for traditional fuel. Imagine spacecraft that glide through space on magnetic waves, powered by fields so precise and efficient that they make today's engines look primitive by comparison. Theoretically, monopole-based systems could offer a clean, nearly limitless source of propulsion, with applications ranging from interplanetary travel to interstellar exploration. But here's the catch: magnetic monopoles are still purely theoretical. Despite extensive searches in particle accelerators and cosmic ray experiments, no one has found definitive evidence of their existence. Some theories suggest they may have formed in the early universe during the extreme conditions of the Big Bang, but if they did, they've either decayed or are so rare that detecting them is next to impossible. Others argue that monopoles might exist in higher dimensions or be hidden in ways we haven't yet imagined. Until we have concrete evidence, the idea of monopole-based propulsion remains speculative, a fascinating possibility, but one that's still far from reality. Even so, the concept of magnetic monopoles sparks the imagination and challenges us to think differently about the forces that govern the universe. They remind us that there's still so much we don't understand, and that the answers to our greatest challenges might lie in the most unexpected places. But while monopoles offer one intriguing path to reimagining propulsion, other theories focus on forces we already know, forces that might be just as transformative if we can learn to control them. What if the empty space around us held a hidden force, one so subtle that it only reveals itself at the smallest scales? This is the essence of the Casimir effect, a quantum phenomenon that might just hold the key to a revolutionary form of propulsion. To understand it, we need to dive into the strange world of quantum mechanics, where even the vacuum of space is alive with activity. At the quantum level, empty space isn't really empty. It's a seething, bubbling sea of virtual particles that pop in and out of existence in an instant. These fleeting fluctuations create a dynamic background of energy, and when two uncharged metal plates are placed incredibly close together, we're talking nanometers apart, they can actually attract each other. This attraction is the Casimir effect, named after Dutch physicist Hendrik Casimir, who first predicted it in 1948. The idea of harnessing this effect for propulsion is both fascinating and ambitious. Imagine a spacecraft equipped with plates that manipulate these quantum forces, creating thrust by exploiting the energy of the vacuum itself. Instead of relying on fuel or external energy sources, the ship would draw power from the very fabric of space, tapping into the universe's hidden energy reserves. It's a concept that feels almost magical, turning the void between atoms into a potential engine for exploration. But the challenges are as immense as the possibilities. The Casimir effect is incredibly weak, detectable only at microscopic scales. Scaling it up to a level where it could propel a spacecraft would require technology far beyond our current capabilities. We'd need to engineer materials and mechanisms that can precisely control and amplify these quantum forces, all while maintaining stability over vast distances. And even if we could achieve this, the energy output might still be too small to make a practical difference for large-scale propulsion. Despite these hurdles, the Casimir effect represents a tantalizing glimpse into the future of space travel. It challenges us to think differently about the universe and the forces that govern it, reminding us that even the emptiest spaces might hold untapped potential. While the idea of Casimir propulsion remains speculative, it's a testament to human ingenuity and our relentless drive to explore the unknown. As we shift our focus from the quantum realm to something more tangible, let's explore a theory that doesn't rely on the strange rules of quantum mechanics, but instead draws inspiration from the natural world. Sometimes the answers to our greatest challenges can be found by looking to the forces and patterns that surround us every day. What if the secret to interstellar travel wasn't about moving faster through space, but about slowing down time itself? This is the intriguing premise behind time dilation drives, a concept that turns one of Einstein's most famous predictions into a potential engine for exploration. According to Einstein's theory of relativity, time doesn't tick at the same rate for everyone. The faster you move, the slower time passes for you relative to someone standing still. This phenomenon, known as time dilation, becomes more pronounced as you approach the speed of light. For a spacecraft traveling at near light speeds, time on board would slow dramatically compared to time on Earth. A journey that takes decades for observers back home might feel like just a few years for the crew. The idea of using time dilation for space travel isn't about breaking the speed of light. It's about bending the rules of time to make interstellar voyages more practical. Imagine a spacecraft accelerating to 99.9% the speed of light. For the crew, the trip to a star system 10 light-years away might take just a few years due to time dilation, while on Earth 10 years would have passed. This means the crew could effectively travel faster than light from their perspective, even though the ship never exceeds light speed. It's a clever workaround that leverages the universe's own rules to shrink the vast distances between stars. But here's the catch: time dilation doesn't solve all the problems of interstellar travel. While the crew might experience a shorter journey, the energy required to accelerate a spacecraft to such speeds is staggering. Even with advanced propulsion systems, the fuel demands and engineering challenges are immense. And then there's the question of causality. What happens when you return to Earth after a trip where time has passed differently for you and everyone else? The crew might return to a world that's decades or even centuries older, raising profound questions about the nature of time and the connections we hold dear. Despite these challenges, the concept of time dilation drive sparks the imagination. It's a reminder that the universe is full of surprises, and that the solutions to our greatest challenges might lie in understanding its deepest mysteries. By manipulating time itself, we could one day make the stars feel a little closer, not by racing against the speed of light, but by riding the waves of relativity. But what if there's another way to shrink the distances between stars, not by slowing time, but by warping space itself? That's where our next theory takes us, into a realm where the fabric of the universe becomes a tool for exploration. What if the universe we see is just the tip of the iceberg, a three-dimensional slice of a much larger, more complex reality? This is the idea behind hyperspace travel, a concept that suggests the existence of higher dimensions could offer shortcuts through the cosmos. Imagine a world where the vast distances between stars are no longer a barrier, where we could fold space itself to travel from one point to another in the blink of an eye. It's a vision straight out of science fiction, but one that's rooted in some of the most cutting-edge theories in physics, particularly string theory. String theory, a framework that attempts to unify all fundamental forces of nature, proposes that the universe isn't just made up of the three spatial dimensions we're familiar with: length, width, and height, but rather 10 or even 11 dimensions. These extra dimensions are thought to be curled up and hidden, far too small for us to perceive directly. Yet, if they exist, they could open up entirely new possibilities for travel. Hyperspace, in this context, would be a higher dimensional realm where the rules of our three-dimensional universe no longer apply. By navigating through these extra dimensions, a spacecraft might bypass the limitations of space and time, effectively creating shortcuts through the cosmos. The concept is as thrilling as it is speculative. If hyperspace exists, it could revolutionize space travel, making interstellar voyages not just feasible but routine. Picture a ship entering a higher dimensional portal, emerging light years away in a fraction of the time it would take to travel through conventional space. It's a vision that captures the imagination, but one that comes with enormous challenges. For starters, we have no direct evidence that these extra dimensions exist. While string theory provides a mathematical framework for their existence, proving it experimentally is another matter entirely. The energy scales required to probe these dimensions are far beyond anything we can currently achieve, leaving the idea of hyperspace firmly in the realm of theory. Even if we could confirm the existence of higher dimensions, navigating them would be a monumental task. How do you map a realm that's invisible to us? How do you ensure a spacecraft doesn't get lost in dimensions we can't see or understand? And what happens if something goes wrong in a space governed by entirely different laws of physics? These are the kinds of questions that keep physicists and engineers up at night, reminding us that every leap forward comes with its own set of risks and unknowns. Despite the speculative nature of hyperspace travel, it's an idea that pushes the boundaries of what we think is possible. It challenges us to think beyond the three dimensions we know and explore the hidden layers of reality. And while the concept remains unproven, it's a reminder that the universe is full of mysteries waiting to be unlocked. But hyperspace isn't the only way to rethink the rules of space travel. While it invites us to explore higher dimensions, other theories focus on manipulating the dimensions we already know, bending and shaping them to our advantage. As we turn our attention to these ideas, we're reminded that sometimes the most groundbreaking discoveries come not from looking beyond what we know, but from seeing the familiar in a completely new light. What if the empty space around us wasn't truly empty, but brimming with untapped energy? This is the intriguing premise behind zero-point energy, a concept that dives into the strange and fascinating world of quantum mechanics. Even in the deepest vacuum of space, where it seems like nothing exists, quantum physics tells us there's still energy, the lowest possible energy state of a quantum system. This energy, known as zero-point energy, is the result of tiny, constant fluctuations in the quantum field, where particles and antiparticles pop in and out of existence in a chaotic dance. It's as if the universe itself is alive with activity, even in its quietest moments. The idea of harnessing zero-point energy for propulsion is as bold as it is speculative. If we could extract even a fraction of this energy, it could provide an almost limitless power source for spacecraft, eliminating the need for traditional fuel. Imagine a ship gliding through the cosmos, powered not by rockets or solar sails, but by the very fabric of space itself. It's a vision that feels both futuristic and poetic, turning the universe's hidden energy into a tool for exploration. But here's the challenge: zero-point energy is incredibly difficult to detect, let alone harness. These quantum fluctuations are incredibly small and fleeting, making them nearly impossible to capture in a practical way. Current theories suggest that extracting usable energy from the quantum vacuum would require technology far beyond our current capabilities, including devices capable of manipulating quantum fields on an unprecedented scale. Some researchers have proposed using advanced materials or exotic configurations of electromagnetic fields to tap into this energy, but these ideas remain purely speculative. The speculative nature of zero-point energy propulsion doesn't stop it from sparking the imagination. It's a reminder that the universe is full of hidden potentials, waiting for us to find creative ways to unlock them. Even if we never succeed in harnessing zero-point energy, the idea challenges us to think differently about the cosmos and the resources it might offer. It's a testament to human ingenuity and our relentless drive to explore the unknown. As we shift our focus from the quantum realm to something more tangible, let's explore a theory that doesn't rely on the strange rules of quantum mechanics, but instead draws inspiration from the natural world. Sometimes the answers to our greatest challenges can be found by looking to the forces and patterns that surround us every day. What if the future of space travel wasn't powered by flames and explosions, but by the gentle hum of charged particles? Enter plasma propulsion, a cutting-edge technology that uses ionized gas or plasma to generate thrust with remarkable efficiency. Unlike traditional chemical rockets that burn through massive amounts of fuel, plasma propulsion systems operate on a different principle. By accelerating charged particles to incredibly high speeds using electric or magnetic fields, these engines can achieve much greater fuel efficiency, making them ideal for long-duration missions where carrying heavy fuel loads isn't practical. The beauty of plasma propulsion lies in its simplicity and elegance. Instead of relying on the brute force of chemical reactions, it taps into the power of electromagnetism. A typical plasma engine works by ionizing a gas, usually xenon, turning it into a cloud of charged particles. These particles are then accelerated by electric fields, creating a high-speed jet of plasma that propels the spacecraft forward. While the thrust generated is relatively low compared to chemical rockets, plasma engines can operate continuously for months or even years, gradually building up incredible speeds over time. One of the most notable examples of plasma propulsion in action is NASA's Dawn mission. Launched in 2007, Dawn used ion thrusters to explore the asteroid Vesta and the dwarf planet Ceres. Over the course of its mission, Dawn's plasma engines accumulated more than 5.5 years of thrusting time, demonstrating the potential of this technology for deep space exploration. The mission showcased how plasma propulsion could enable spacecraft to travel farther and faster than ever before, all while using a fraction of the fuel required by traditional systems. But plasma propulsion isn't without its challenges. One of the biggest limitations is its dependence on external power sources. Unlike chemical rockets, which carry their energy in the form of fuel, plasma engines require a steady supply of electricity, usually from solar panels or nuclear reactors. This means their effectiveness diminishes as a spacecraft moves farther from the sun or into regions where sunlight is scarce. Additionally, while plasma engines are highly efficient, their low thrust makes them less suitable for missions that require rapid acceleration or maneuvering, such as launching from a planet's surface. Despite these limitations, plasma propulsion represents a significant leap forward in how we think about space travel. It's a technology that prioritizes efficiency and sustainability, offering a glimpse of what's possible when we move beyond the limitations of chemical rockets. But what if there were a way to generate propulsion without relying on fuel or external power sources at all? What if the key to interstellar travel lies in something even more unconventional? That's where our next theory takes us into a realm where the rules of propulsion are rewritten entirely. What if you could cross an insurmountable barrier without ever having to climb over it? This is the essence of quantum tunneling, a phenomenon that allows particles to pass through obstacles they shouldn't, in theory, be able to breach. At the quantum level, particles like electrons don't behave like tiny billiard balls. Instead, they exist as probability waves with the potential to appear on either side of a barrier, even if they don't have the energy to overcome it. It's as if they're playing a cosmic game of hide and seek, vanishing and reappearing in ways that defy classical physics. The implications of quantum tunneling are profound, not just for understanding the subatomic world, but for reimagining how we might traverse vast distances in space. Imagine a spacecraft equipped with a quantum tunneling drive capable of jumping through barriers in spacetime itself. Instead of traveling through the vast emptiness between stars, the ship could, in theory, bypass those distances entirely, appearing at its destination as if it had teleported. It's a concept that feels straight out of science fiction, but it's rooted in the same principles that govern the behavior of particles at the smallest scales. So, how might this work? One speculative idea involves creating a kind of quantum tunnel, a controlled pathway through space-time that a spacecraft could pass through. The ship wouldn't need to accelerate to incredible speeds or rely on massive amounts of fuel. Instead, it would simply step through the barrier, emerging on the other side in an instant. Theoretically, this could make interstellar travel not just faster but instantaneous. It's a tantalizing vision, one that could revolutionize our understanding of propulsion and the nature of space itself. But here's the catch: quantum tunneling is inherently unpredictable. It works beautifully for individual particles, but scaling it up to the size of a spacecraft is a monumental challenge. The energy required to create and stabilize a quantum tunnel large enough for a ship would likely be beyond anything we can currently imagine. And even if we could achieve it, there's no guarantee that the ship would emerge intact or in the right place. The uncertainties of quantum mechanics make this idea as risky as it is revolutionary. Despite these hurdles, the concept of quantum tunneling propulsion sparks the imagination. It's a reminder that the universe operates on rules far stranger than we often realize, and that the solutions to our greatest challenges might lie in the most unexpected places. While the practical application of quantum tunneling for space travel remains speculative, it opens the door to a world of possibilities, challenging us to think beyond the limitations of conventional physics. As we consider the potential of quantum tunneling, it's worth reflecting on how it shifts our perspective on space and time. Instead of seeing the universe as a vast, empty expanse, we might begin to view it as a dynamic, interconnected web, full of hidden pathways waiting to be discovered. And while quantum tunneling offers one intriguing possibility, other theories take a different approach, focusing not on bypassing barriers, but on reshaping the very fabric of space-time itself. That's where our journey takes us next, into a realm where the rules of the cosmos might be rewritten entirely. What if the fabric of space-time wasn't smooth and continuous, but more like a frothy, bubbling sea at the smallest scales? This is the essence of space-time foam, a concept that suggests the universe might not be the orderly, predictable place we imagine. At scales so tiny they're almost beyond comprehension, space and time could be fluctuating wildly, creating a chaotic, foam-like structure. These fluctuations, sometimes called quantum foam, are thought to be the result of the constant churn of particles and energy at the quantum level, where the rules of physics as we know them break down. The idea of space-time foam isn't just a fascinating thought experiment. It could have profound implications for space travel. If space-time is indeed frothy at these tiny scales, could we find a way to navigate through these fluctuations? Imagine a spacecraft designed to ride the quantum foam, using the chaotic fluctuations to propel itself forward. Instead of traveling through smooth, continuous space, the ship would navigate a turbulent, ever-changing landscape, potentially bypassing the limitations of conventional propulsion. It's a vision that feels almost surreal, like sailing through a cosmic storm instead of calm waters. But here's the challenge: space-time foam, if it exists, operates at scales far smaller than anything we can currently observe or measure. The Planck scale, where these fluctuations are thought to occur, is so minuscule that probing it directly is beyond our current technological capabilities. Even detecting indirect evidence of space-time foam would require breakthroughs in both physics and instrumentation, leaving the concept firmly in the realm of theory. And even if we could confirm its existence, navigating through it would be a monumental task. How do you steer a spacecraft through a chaotic, unpredictable medium? How do you ensure it doesn't get torn apart by the violent fluctuations of space-time itself? Despite these hurdles, the concept of space-time foam sparks the imagination. It's a reminder that the universe might be far stranger and more dynamic than we ever imagined, even at its most fundamental levels. It challenges us to think beyond the smooth, continuous space-time of Einstein's relativity and explore the chaotic, quantum nature of the cosmos. While the idea of using space-time foam for propulsion remains speculative, it's a testament to the boundless creativity of human thought and our relentless drive to explore the unknown. As we leave the frothy, fluctuating realm of space-time foam behind, let's turn our attention to a theory that doesn't rely on quantum fluctuations or chaotic structures. Sometimes the answers to our greatest challenges come not from diving into the smallest scales, but from looking at the universe in a completely new light. That's where our next idea takes us into a realm where the very fabric of reality might hold the key to unlocking the stars. What if the key to interstellar travel wasn't about carrying fuel, but about harnessing the power of light itself? This is the promise of photonic propulsion, a technology that uses photons, the tiny particles of light, to generate thrust. Unlike traditional rockets that rely on burning fuel, photonic propulsion taps into the momentum of light itself, offering a clean, fuel-free way to explore the cosmos. It's a concept that feels almost magical, turning something as intangible as light into a tangible force for movement. At its core, photonic propulsion works by reflecting or absorbing photons to create a tiny but continuous push. When light strikes a surface, it transfers momentum, just like a ball bouncing off a wall. Over time, this gentle pressure can add up, accelerating a spacecraft to incredible speeds. The real beauty of this method lies in its simplicity. Instead of carrying massive amounts of fuel, a spacecraft equipped with a reflective sail could be propelled by beams of light, whether from powerful lasers or even sunlight. It's a bit like sailing on a cosmic wind, but instead of air, the sail catches the force of photons. One of the most exciting applications of photonic propulsion is the idea of laser-driven interstellar probes. Projects like Breakthrough Starshot aim to send tiny, lightweight spacecraft to nearby star systems using powerful ground-based lasers. By focusing intense beams of light onto reflective sails, these probes could reach speeds of up to 20% the speed of light, making the journey to Alpha Centauri, our nearest stellar neighbor, a matter of decades rather than millennia. It's a bold vision that challenges us to rethink how we approach space travel, moving beyond the limitations of chemical rockets and embracing the power of light. But photonic propulsion isn't without its challenges. One major limitation is its dependence on powerful light sources. For interstellar missions, the lasers required would need to be unimaginably strong, demanding vast amounts of energy and infrastructure. Solar sails, which rely on sunlight, are only effective close to stars, making them less practical for journeys into the depths of interstellar space. Additionally, the materials used for the sails must be incredibly lightweight yet durable enough to withstand the intense pressure of laser beams without melting or tearing. Even the slightest imperfection could spell disaster, sending a probe spinning off course or disintegrating entirely. Despite these hurdles, photonic propulsion represents a significant leap forward in how we think about space travel. It's a technology that prioritizes efficiency and sustainability, offering a glimpse of what's possible when we move beyond the constraints of traditional propulsion systems. By harnessing the power of light, we could one day unlock the stars in ways that were once thought impossible. But what if there's a way to travel through the cosmos without relying on light at all? What if the key to interstellar exploration lies in something even more elusive, a force or phenomenon that doesn't require beams or sails? That's where our next theory takes us, into a realm where the rules of propulsion are rewritten entirely, offering a vision of space travel that's as unconventional as it is thrilling. What if the force that keeps us grounded on Earth could be harnessed to propel us through the cosmos? Artificial gravity, a concept often associated with spinning space stations and sci-fi movies, might hold the key to a revolutionary form of propulsion. At its core, the idea revolves around manipulating inertia, the tendency of objects to resist changes in motion. By creating artificial gravity, we could theoretically generate thrust without relying on traditional engines or fuel, opening up entirely new possibilities for space travel. The theoretical basis for this idea lies in Einstein's equivalence principle, which states that the effects of gravity and acceleration are indistinguishable. If we can create a controlled gravitational field, we might be able to use it to push a spacecraft forward. Picture a ship equipped with a device that generates artificial gravity in a specific direction, effectively pulling the vessel along without the need for expelling mass. It's a concept that feels almost magical, turning the force that binds planets and stars into a tool for exploration. One speculative approach to artificial gravity propulsion involves using rotating masses or advanced materials that can produce localized gravitational fields. For example, a spacecraft might employ rapidly spinning super-dense objects like neutronium or other exotic matter to create a directional gravitational pull. Theoretically, this could generate continuous thrust, allowing the ship to accelerate steadily over time. Another idea involves manipulating gravitational waves, ripples in space-time caused by massive objects, to create a kind of gravitational sail that catches these waves and propels the vessel forward. However, the challenges are as immense as the potential. Creating artificial gravity on a scale large enough to propel a spacecraft is far beyond our current capabilities. The energy requirements alone would be staggering, and we'd need materials and technologies that don't yet exist. Even if we could generate such a field, controlling it with precision would be a monumental task. And then there's the question of feasibility. Does the physics of artificial gravity propulsion hold up under scrutiny, or is it purely speculative? These are the kinds of questions that keep physicists and engineers debating the idea's practicality. Despite the hurdles, the concept of artificial gravity propulsion sparks the imagination. It challenges us to think differently about the forces that govern the universe, turning something as familiar as gravity into a potential engine for exploration. While the idea remains speculative, it's a reminder that the cosmos is full of untapped potential, and that the answers to our greatest challenges might lie in the most unexpected places. As we leave the realm of artificial gravity behind, let's turn our attention to an even more profound idea: the manipulation of space-time itself. While artificial gravity focuses on harnessing a familiar force, other theories invite us to reshape the very fabric of reality, offering possibilities that could redefine how we explore the stars. What if the universe itself had built-in highways, invisible threads woven into the fabric of space-time that could carry us across unimaginable distances? This is the idea behind cosmic strings, hypothetical one-dimensional defects in the structure of the cosmos. Think of them as cracks or wrinkles in space-time, remnants of the early universe when it was still cooling and settling into its current form. These strings, if they exist, would be unimaginably thin, just one atom wide, but stretch across billions of light years, forming a cosmic web that connects distant corners of the universe. The concept of cosmic strings isn't just a wild idea. It's rooted in the mathematics of theoretical physics, particularly in models of the early universe. According to some theories, these strings could have formed during the rapid expansion of space-time just moments after the Big Bang. Unlike black holes or stars, cosmic strings don't have mass in the traditional sense. Instead, their immense gravitational influence comes from their extreme density and tension, creating ripples in space-time that could, in theory, be harnessed for propulsion. So how might we ride these cosmic strings? One speculative idea involves using a spacecraft to latch onto a string's gravitational field, effectively surfing its immense tension to achieve incredible speeds. Imagine a ship gliding along a cosmic thread, propelled not by engines or fuel, but by the natural energy of the universe itself. In theory, this could allow for faster-than-light travel without violating the laws of physics, as the ship itself wouldn't be moving through space, it would be carried along by the string's distortion of space-time. It's a concept that feels almost poetic, turning the universe's own structure into a tool for exploration. But here's the catch: cosmic strings are entirely hypothetical. Despite decades of searching, we've never observed one directly. Their existence is predicted by certain models of the early universe, but confirming their presence would require detecting their gravitational effects or the ripples they create in the cosmic microwave background. Even if we did find evidence of cosmic strings, the practical challenges of using them for propulsion would be staggering. How do you locate and navigate a thread that's billions of light years long? How do you ensure a spacecraft doesn't get torn apart by the immense gravitational forces at play? These are the kinds of questions that make cosmic string propulsion a tantalizing but distant possibility. Despite the speculative nature of this theory, cosmic strings spark the imagination. They remind us that the universe might be far more intricate and interconnected than we ever imagined, with hidden pathways waiting to be discovered. And while the idea of riding cosmic strings remains a dream for now, it's a testament to the boundless creativity of human thought and our relentless drive to explore the unknown. But what if the key to interstellar travel doesn't lie in the grand structures of the cosmos, but in something far more subtle, a force or phenomenon that operates on a scale we're only beginning to understand? That's where our next theory takes us, into a realm where the smallest interactions might hold the key to the grandest journeys. What if the universe held a type of matter so strange that it defies everything we know about physics? Enter exotic matter, a theoretical substance with properties that seem to bend or even break the rules of nature. Unlike ordinary matter, which has positive mass and energy, exotic matter possesses negative energy or mass, making it a fascinating and controversial topic in the world of physics. This isn't just a quirky thought experiment. Exotic matter could hold the key to some of the most ambitious propulsion concepts ever imagined. One of the most exciting applications of exotic matter lies in its potential to stabilize wormholes. As we've explored earlier, wormholes are hypothetical tunnels through space-time that could connect distant points in the universe. But there's a problem. Wormholes are incredibly unstable and would collapse almost instantly under their own gravitational forces. Exotic matter, with its negative energy density, could theoretically counteract this instability, holding the wormhole open long enough for a spacecraft to pass through. It's like using a cosmic jack to prop open a doorway between stars. Exotic matter also plays a starring role in the Alcubierre Drive, a concept for faster-than-light travel that warps space-time around a ship. To create the necessary space-time distortion, the drive would need exotic matter to generate the negative energy required. Without it, the warp bubble would collapse, making the Alcubierre Drive impossible. In this way, exotic matter isn't just a supporting player, it's the foundation of some of the most revolutionary ideas in propulsion. But here's the catch: exotic matter is purely theoretical. We've never observed it in nature, and creating it in a lab would require breakthroughs in quantum physics and energy manipulation. Some theories suggest that exotic matter could exist in the form of quantum fields or particles, but detecting or producing it remains a monumental challenge. Even if we could, the properties of exotic matter are so bizarre that we'd need entirely new frameworks to understand and control it. The very idea of negative mass or energy raises profound questions about the nature of reality and the limits of our scientific knowledge. Despite these hurdles, the concept of exotic matter sparks the imagination. It challenges us to rethink the rules of physics and explore possibilities that once seemed impossible. While the practical applications remain speculative, the pursuit of exotic matter pushes the boundaries of what we think is achievable, reminding us that the universe is full of mysteries waiting to be unlocked. As we reflect on the potential of exotic matter, it's worth considering that the answers to our greatest challenges might not lie in defying the laws of physics, but in reimagining them. What if the key to interstellar travel isn't about creating exotic materials, but about leveraging forces we already know, forces that might be just as transformative if we can learn to control them? That's where our next theory takes us, into a realm where the familiar becomes extraordinary. What if the universe we live in is just one of countless others, each with its own set of laws and possibilities? This is the tantalizing idea behind interdimensional travel, a concept that doesn't just push the boundaries of space travel but redefines the very notion of reality itself. Instead of traversing vast distances within our universe, interdimensional travel proposes leaping into parallel realities, where the constraints of time and space as we know them might not even apply. It's a mind-bending idea, one that blends science fiction with cutting-edge theoretical physics. The roots of interdimensional travel lie in two of the most intriguing ideas in modern science: string theory and the multiverse hypothesis. String theory suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in a higher dimensional space, far beyond the 3 dimensions we experience. Some versions of the theory propose the existence of up to 10 or 11 dimensions, most of which are curled up and hidden from our perception. The multiverse hypothesis takes this a step further, suggesting that our universe is just one of many, each occupying its own bubble in a vast cosmic foam. Together, these ideas open the door to the possibility of traveling between dimensions or even universes. So, how might interdimensional travel work? One speculative idea involves creating a bridge between dimensions, perhaps by manipulating the hidden higher dimensions predicted by string theory. Imagine a spacecraft equipped with a device that could tune into these extra dimensions, opening a portal to another reality. Instead of traveling through space, the ship would simply step through this doorway, emerging in a completely different universe. It's a concept that feels straight out of science fiction, but it's grounded in the same mathematical frameworks that physicists use to describe the nature of reality. Of course, the challenges are as immense as the possibilities. For starters, we have no direct evidence that these extra dimensions or parallel universes exist. While string theory and the multiverse hypothesis provide compelling mathematical models, proving their existence experimentally is another matter entirely. Even if we could confirm their reality, navigating them would be a monumental task. How do you map a dimension you can't see or understand? How do you ensure a spacecraft doesn't get lost in a reality with entirely different physical laws? These are the kinds of questions that make interdimensional travel as daunting as it is fascinating. Yet, the idea sparks the imagination, offering a glimpse of a universe far richer and more complex than we ever imagined. It challenges us to think beyond the confines of our own reality and consider the possibility of worlds beyond our wildest dreams. While the practical application of interdimensional travel remains firmly in the realm of speculation, it's a reminder that the universe is full of mysteries waiting to be unlocked. As we reflect on the implications of interdimensional travel, it's worth considering how these theories reshape our understanding of space, time, and reality itself. They invite us to think bigger, to imagine not just new ways of exploring the cosmos, but entirely new ways of existing within it. And while the journey to these parallel realities may remain a dream for now, the pursuit of these ideas pushes the boundaries of what we think is possible, reminding us that the universe is far stranger and more wondrous than we ever imagined. But what does all of this mean for the future of space travel and for humanity itself? As we've explored these 26 unconventional theories, one thing becomes clear: the universe is full of possibilities, each more astonishing than the last. From bending spacetime to riding cosmic strings, from harnessing the quantum vacuum to leaping into parallel dimensions, the ideas we've discussed challenge us to rethink not just how we travel, but how we see the cosmos. And while many of these concepts remain speculative, they remind us that the journey to the stars is as much about imagination as it is about science. So, as we close this exploration, let's take a moment to reflect on the extraordinary potential of these ideas and the boundless curiosity that drives us to reach for the stars. As we wrap up this journey through 25 unconventional theories on propulsion beyond light speed, it's impossible not to be struck by the sheer creativity and audacity of these ideas. From bending spacetime with warp drives to surfing gravitational waves, from harnessing the quantum vacuum to leaping into parallel dimensions, each concept pushes the boundaries of what we thought was possible. These theories aren't just flights of fancy, they're bold, imaginative leaps that challenge our understanding of physics, space, and time itself. They remind us that the universe is far stranger and more wondrous than we often give it credit for. Yet, for all their brilliance, these ideas come with enormous challenges. Many are purely speculative, relying on phenomena we've yet to observe or technologies that don't yet exist. Concepts like exotic matter, quantum tunneling, and cosmic strings stretch the limits of our scientific knowledge, demanding breakthroughs that could take decades or even centuries to achieve. But that's the beauty of these theories. They inspire us to dream bigger, to question the rules we thought were unbreakable, and to imagine a future where the impossible becomes possible. What makes these ideas so powerful isn't just their potential to revolutionize space travel, it's their ability to ignite our collective imagination. They remind us that exploration isn't just about reaching new destinations, it's about expanding our understanding of what it means to be human. Every theory we've explored today, no matter how far-fetched, represents a step forward in our quest to unlock the secrets of the cosmos. They challenge us to think beyond the horizon, to see the universe not as a static backdrop, but as a dynamic, ever-changing tapestry of possibilities. So, as we close this chapter, let's take a moment to reflect on the future these theories could bring. Imagine a world where interstellar travel isn't just the stuff of science fiction, but a tangible reality. Picture humanity venturing to distant star systems, not as a distant dream, but as a shared achievement. Which of these ideas excites you the most? Could it be the elegance of solar sails, the audacity of black hole drives, or the mind-bending potential of interdimensional travel? Share your thoughts in the comments below, because the future of space exploration isn't just shaped by scientists and engineers, it's shaped by dreamers like you. As we look to the stars, let's remember the words of Carl Sagan: "Somewhere, something incredible is waiting to be known." These theories remind us that the universe is full of incredible possibilities, waiting for us to discover them. The journey ahead is as vast and uncharted as the cosmos itself, but with curiosity, creativity, and courage, there's no limit to what we can achieve. So let's keep dreaming, keep exploring, and keep reaching for the stars, because the future of space travel is only just beginning.